All right, welcome back on to chapter 5. Today we're going to talk about eigenvectors and eigenvalues. So before we begin, if you are coming into this lesson and you have not done 4.9, okay, learning about Markov chains, stop. Do not go past go, do not collect $200, go back and review 4.9. Maybe have the filled notes up on the side as well so you can get a good handle on how this is related to 4.9, what we just did. Also, if you are really bad at finding the null space or finding a basis for the null space, stop. Go back, review what the null space is and how to find the basis for a null space. That is really, really important to this lesson. In fact, it's so crucial to this lesson that you cannot do this lesson without learning about the null space. So if either of those things apply to you, stop, come back to this later, go back and review the null space, review 4.9, and then come back to this. Because what we're doing in chapter 5 is we are looking at a very specific transformation. So remember, a transformation can be represented by multiplying a vector, an input vector, by a matrix A that does all the transformations we're looking for. So that the vector we put in changes into the result after I've multiplied that vector times A. Okay, a lot of times that's mapping the vector to no location. Maybe it's rotating it, maybe it's scaling it, something like a combination of many of these things. But we are specifically going to look at a transformation where the vector is scaled by a constant, okay? And not each entry is scaled by a different constant, but the whole vector is scaled by the same constant, okay? So that could change the length or it could change the direction. Those are the only two things that this transformation that we're going to look at today does, okay? So if this is going to happen, aka if we multiply a vector by a matrix, and the only thing that changes is either the length of the vector, okay, the whole vector was scaled by one number, or it was pointed in the opposite direction, which is the same as the whole vector was scaled by a negative. Okay, this is what we call an eigenvector. Key point here, this is only for square matrices, and that's really important to how we're going to end up finding these eigenvalues or eigenvectors. So an eigenvector of a square matrix is another key point, non-zero vector. An eigenvector cannot be the zero vector, okay? If we multiply the zero vector by a matrix A, what's going to come out? The zero vector, duh. Okay, so we're only looking at non-zero vectors. The zero vector is not special because we know it will do the same thing for every single matrix that it's multiplied by. Multiplying the zero vector by a matrix results in 0, the end. Okay, not interesting. So an eigenvector of a square matrix, okay, it's going to be associated with a specific square matrix, is a non-zero vector such that when I multiply that vector by the matrix, I get some scalar, lambda, times that vector. Okay, the only thing that changed was that vector got scaled by some number. Okay, that specific scalar is called an eigenvalue of A. Okay, and that's again, in order to be an eigenvalue, there has to be a non-trivial, meaning non-zero vector solution to ax equals lambda times that same x we multiplied over here. Okay, so again, in other words, a non-zero vector is an eigenvector if and only if, this is a bidirectional statement, the transformed vector ax points in the same or the opposite direction of v. Basically, it's an eigenvector if after the transformation, your vector does not change direction. Okay, it's in this, or it goes along the same line, I guess, if we're thinking about it kind of in a three-dimensional or two-dimensional way. Okay, this is exactly what we did in 4.9. In Markov chains, when we were looking at this, we were asking ourselves, what is my steady state vector? What is the vector I will multiply by A such that the vector does not change after it comes out? Okay, this is an eigenvector, and the eigenvalue would be lambda equals 1. Okay, so our steady state vector that we learned about in 4.9 is in fact an eigenvector of A with an corresponding eigenvalue of 1. Now, there will be different eigenvalues for the same matrix, and there will be different eigenvectors that correspond to each different eigenvalue. We're going to get into how to find those and how they correspond later. Let's first just work on testing is our vectors eigenvectors of A. So if I ask you if u or v is an eigenvector of A, I'm asking you, if I multiply A times U, will I get a constant times U? Okay, we'll just start with U for now. And we can do V in a second. So if I multiply A times U, will I get a constant? Like, will I have scaled U by some constant? It has to be the same constant for both components. So when I multiply this, I'm going to get 0 minus 2, and then I will get negative 4 plus 2. So that's the vector negative 2, negative 2. So my conclusion is yes, U is an eigenvector of A, specifically of this matrix, with a corresponding eigenvalue of lambda equals negative 2. Because if I multiplied this vector by negative 2, I would get the output vector. Okay, and let's test, and notice that this eigenvector corresponds to this specific eigenvalue. That will be important. Okay, they are related, they are not, you can't break them apart. So then, is V an eigenvector? So again, I'm asking myself, if I multiply V times A, will I get a constant times V? Okay, so A, again, is 0, negative 4, negative 2, 2, times the vector negative 1, 1. And when I multiply that together, I am getting 0 minus 2, but then I'm getting 4 plus 2. So this is the vector negative 2, 6. There is no constant I could multiply negative 1, 1 by to get me, no one whole constant I could scale the vector by. No lambda times negative 1, 1 would be equal to negative 2, 6. Okay? This will not equal this for any lambda. Okay? Therefore, V is not an eigenvector of A. Okay? So testing whether or not something is an eigenvector means if I multiply this vector times the matrix I was given, will that just scale the vector? Okay, notice that this doesn't look like the matrix transformation we're used to, where we're just scaling everything by a constant. Okay, we were used to kind of a diagonal square matrix that would do that, but it happens that we could have other types of matrices with different entries that can have eigenvectors for specific vectors. Okay, the way we did it before was we had a matrix A, let's say that was a diagonal matrix that just had the vector, or excuse me, the scalars we wanted to scale everything by on the diagonal. Okay, and that's an example where everything would count as an eigenvector for this matrix because everything gets scaled by negative 2. But here, if I look at this matrix, only a certain number of vectors are going to be eigenvectors because a scalar operation like this will only happen for a certain number of vectors, like U, but not V. Does that make sense? Hopefully. Okay. If you have questions about that, tell me to come back to this point in office hours. Okay. So let's take a look at what's next. So how do I find maybe all of the eigenvectors? Because we were able to just kind of test one. Okay. How do I find eigenvectors? How do I find an eigenvalue? And we're actually going to go into finding all the eigenvalues for all square matrices next time. But today we're just going to say, okay, how do I find, given a specific eigenvalue, how do I find all the eigenvectors that go with that? Okay. Before, on this page, we said, okay, here's an eigenvector, and then we could kind of figure out what the eigenvalue was. This eigenvalue could correspond to more than just this vector, though. It could be that more vectors are associated with this scalar than just U. And we want to know how to find all of them that are associated with this specific eigenvalue, that scalar. Okay, so if lambda is an eigenvalue for the matrix A, then, and this is where 4.9 comes back again, okay, because we started with A equals, oh, dang it, we are looking for, to find an eigenvector, a times x equals lambda times x. So if I want to make an equation that I can solve for lambda, or maybe test out a lot of different x's, I can subtract this to the other side. Ax minus lambda x equals 0. And in order to get to this formula, remember that a multiplicative identity exists. So this equation could also be written as ax minus lambda times the identity matrix times x. Okay? And then I can just, because matrix multiplication is distributive, I can factor out this x. So I'm getting a minus lambda times the identity matrix times x equals 0. And this is more useful because this, and again, we're looking for a non-trivial solution. We're looking for a vector x that is not 0. But this, if you mind me putting this in quotes, and I'll use b instead of a like I usually do, this is finding the solutions x for the equation bx equals 0. This, what we're looking for x values or x vectors that will be a non-trivial solution for this, is we're looking for the null space. What vectors could I put in here that when I multiply them by this weirdo matrix over here that's going on, okay, but it's just a matrix like b, something, okay, what vectors multiplied by this matrix will give me 0? We're looking to solve bx equals 0 or ax equals 0 again. Okay, we're looking for the null space. Okay, so, and since we're looking for the null space, we know that it is a subspace, and then since, again, we're using eigenvectors here, we're going to call this a specific thing. This is the eigenspace. Okay, so we've got the eigenvector, we've got the eigenvalue, we've got the eigenspace, okay, all of the pieces, all together. We're calling them eigen something. Okay, and feel free, I think we looked this up last year, where this root eigen came from, but feel free to Google that, pause here and Google that on your own. So, all right, this will help us because if we are given a very specific value of lambda to find the eigenspace for, we are basically saying, do this little math, find the matrix here, okay, that would go here, some b, maybe, okay, and then find its null space. So this is where if you got all the way up to this point and you're like, yay, I'm ready to go, and you've forgotten, you're like, oh, I'm not so sure what the null space is, pause right now, go back and review what the null space is and how to find it. Okay, in short though, we're just going to solve this equation. Okay, just kind of like we did in chapter 2 or 3. We're going to solve bx equals 0 and write out the solutions. So in this example, we're going to be given an eigenvalue, okay, and find the corresponding eigenvectors. Okay, so again, this, and here's my hint, this is only an eigenvalue if I can find non-trivial solutions to this equation. Okay, so non-zero vector solutions to this equation. All right, so let's start with this, just so we can show this progression again. We want this equation to have non-trivial solutions. That means that ax minus 4x equals 0 should still have non-trivial solutions. Okay, and you can see why we want non-trivial solutions, because we're like, all right, duh, if I put 0 in for x, then 0 equals 0, hooray. It's not what we want, okay, because 0 will always work for this kind of thing. We want to have the interesting solutions, the ones that are not the 0 vector. So if I set it up like I did up here, kind of doing some factoring, this will be that a minus 4 times the identity matrix times x equals 0. Let's take a look at what this matrix is right now. So A is 0, negative 4, negative 2, 2. Okay, I think this is exactly what we did. This is the same matrix from example 1. So we're showing you that there is in fact another eigenvalue other than just negative 2. Okay, and I am subtracting 4 times the identity matrix. So remember that the identity matrix is the one that has 1s all along the diagonal and 0s everywhere else. If I scale that by 4, I'm getting 4s along the diagonal and 0 everywhere else. So this matrix that I'm looking for is really negative 4, negative 4, negative 2, negative 2. Okay, so I want you to stop and take a look at this real quick. If you are up on your linear algebra, you can see that these columns are linearly dependent because they are scalar multiples of each other. That is what we want. We want to get columns that are scalar multiples, that are linearly dependent, because in order for ax, again, bx equals 0 in this case, because I'm using a too often, in order for this to have non-trivial solutions, think back to the invertible matrix theorem, I need there to be free variables. I need there to not be a pivot in every column. So if I have linearly, very obviously, linearly dependent columns, I know I'm doing the right thing because I want there to be free variables. I want there to not be a pivot in every column so that I get non-trivial solutions. Okay, so I know that I'm on the right track right here. So now I'm going to take this, okay, because this is this matrix, so I'm asking myself, what are the solutions to this equation? Okay, and to find the solutions, I'm going to row reduce. Okay, and when I row reduce, and notice I'm not writing A and then row reducing A. I'm row reducing A minus the eigenvalue times I. Okay, took me one step. I think I did 2 steps, whatever. Row reduced echelon form is going to be 1, 0, 1/2, 0. Okay, you could probably do that in your head. So what solutions come out of here? Well, this is that x1 equals negative 1/2 x2. Okay, remember that this was equal to 0, and then I subtracted the 1/2 x2 to the other side. So I need the corresponding eigenvectors, which means I want to I should write x2 is free. I want the vector solutions to this equation. So that means my solutions, x, are going to be, okay, I've got 2 variables here, so negative 1/2, 1. They are all going to be scalar multiples of this vector right here. Okay, and we can even check, and I think I did, and I won't because we're already well into this video, but to check that this is an eigenvector corresponding to the eigenvalue of 4, then I can multiply this vector times the original matrix and see if I get 4 times this vector out. That's what should be true. But notice that this, okay, is providing me all of the corresponding eigenvectors to lambda equals 4. This is an infinite number of vectors corresponding to lambda equals 4. Okay, and what's important is this, the span of this one vector, all linear combinations of this one vector, are going to give me, are going to be eigenvectors corresponding to lambda equals 4. So what I'm really getting at here is this, okay, the basis that describes the eigenspace corresponding to lambda equals 4. Okay, so basis for the lambda equals 4 eigenspace, and I'm being very specific because we checked on in example 1, I'll come back to it real quick. When we were checking over here, we got a different eigenvalue for a different type of vector for 1, 1. So there will be a totally different eigenspace for this specific vector. And we are only describing right now, we are describing the eigenspace corresponding to this eigenvalue. So the basis for the eigenspace corresponding to lambda equals 4 is all linear combinations, in this case, all scalar multiples of the vector negative 1/2, 1. So let's do this for something that's a little bit more complicated. Let's expand it into a 3×3. Okay, so we're again, I'm giving you an eigenvalue, and next lesson we'll talk about how to find the eigenvalues. But I want you to find a basis for the corresponding eigenspace to lambda equals 2. Again, there could be other eigenspaces for this matrix. We are just going to focus on the one corresponding to lambda equals 2. The other ones will correspond to other eigenvalues. Okay, so first thing we need to do is find the matrix that we were looking to row reduce. I need to find, and I said this was S minus 2i. Okay, that is the matrix that I am looking to find the null space for. So my S minus 2i there we go, minus, okay, this subtraction is what I'm looking for. So I'm getting 0 across the whole top row. Then I'm getting -1, 1, 1. Okay, and then I'm getting -1, 1, and 1. Okay, again, I'm checking myself here. Are all of the columns linearly dependent? Yes. Okay, I can see that column 2 and 3 are a scalar multiple of column 1, so I know that I'm going to get free variables, which is what I wanted. Okay, so if I am solving, just to show you again, and you don't have to write this every time when you're solving, I am trying to find all solutions to this equation, which means I am row reducing this matrix. And when I row reduce, you could do it in like 3 operations, maybe less. You're getting, hey, remember row reducing means I gotta put all my rows of zeros at the bottom. Okay, so I've got 2 free variables, which made sense. We had 2 linearly dependent columns. So I'm getting that x1 equals x2 plus x3. Okay, because again, this was an ax equals 0 equation, so this is only the coefficient matrix, okay, not the augmented matrix. So again, we have 2 free variables, x2 free, x3 free, but if we're looking for a basis, we're looking for a set of vectors. So I need to write the vector, parametric vector solution here. So x equals, okay, x2 is my first free variable. It's going to be 1 times x1, or 1 for x1, 1 for x2, and 0 for x3. x3 is my other free variable, so my vector is going to be 1, 0, 1. Okay. All right, so that means, and these again are, you can see, linearly independent vectors, and the span of these 2 vectors, all linear combinations of these 2 vectors, will be solutions to ax equals 0. The span of these 2 vectors, again, all linear combinations of these 2 vectors, will be eigenvectors for the matrix S, specifically corresponding to the eigenvalue lambda equals 2. So if I, for example, a linear combination of this vector and this vector is me putting a 1 here and a 0 here, so just this. So if I want to test this out, I could take just this vector here, multiply it by S, and I should get 2 times this vector. You could do the same thing with the other vector. So if I'm writing a basis, so the basis for the lambda equals 2 eigenspace is the set of vectors 1, 1, 0 and 1, 0, 1. Okay? All right. Now, a couple more short things, and then I'll leave with some example problems because I don't want to go through all of them. So, okay, key point. This is a big star here. An eigenvalue, lambda, might be 0, meaning I might get that would be any time when ax equals lambda times x, and that's 0. So an eigenvalue could be 0, okay, and that would be just solutions to ax equals 0, okay, without changing a. But an eigenvector is never 0. An eigenvector has to be a non-trivial solution to ax equals 0, okay? A non-trivial solution to a minus lambda I times x equals 0, okay? Obviously, again, an eigenvector is never the 0 vector because obviously putting a 0 here will make the whole thing 0. Okay, we're interested in the more complex solutions, the ones that are not trivial. Okay, all right, so a couple of quick things and a teeny tiny proof. It'll be quick, I promise. So suppose that I have a eigenvalue of a. Now, how do I then determine an eigenvalue of a squared or a cubed? Okay, what would be an eigenvalue of a to the nth power? Can we prove this knowing that lambda is right now an eigenvalue of a? So since lambda is an eigenvalue of a, by definition, I am given the equation that ax equals lambda x. I don't really care what lambda is. I know it's an eigenvalue. That's all I need to know. Now, if I wanted to say what is the eigenvalue of a squared, well, why don't I just square a? Or why don't I multiply by a on both sides? Now, something that we missed on the last test. Matrix multiplication is not commutative. Okay, so whatever is happening on the left side has to, again, happen on the left side. Okay, these are the matrices I just multiplied to this equation. Now, matrix multiplication is associative, so I can say that this is a squared times x. And then on the right side, lambda is a scalar, which means I can factor it to the front. So this is really lambda times ax. Okay, only works because lambda is a scalar. Do not try that with a matrix. Please, please, please. Now, one other thing. We already told you that ax was equal to lambda x. So I'm going to sub that in. So a squared x equals lambda times lambda x, which is a squared x equals lambda squared x. This follows the format we were looking at originally. So this means, therefore, lambda squared is an eigenvalue of a squared. Okay, again, given that lambda is an eigenvalue of a. Okay, and the same would happen. Lambda cubed is an eigenvalue, we would just repeat the process, of a cubed. So finally, if I was given an eigenvalue of a matrix, and I needed to find the eigenvalue of a to the nth power, it's just lambda to the nth power. Now, is it the only eigenvalue? No, but I do know that it is one eigenvalue, which is helpful. Whoop. Now, it may be the only eigenvalue. That's something we'll have to determine next lesson, and how to test that, but it is at least one of the eigenvalues of a to the n. Okay. My teeny proof, to save us time from rewriting, I'm going to use my field notes and just kind of talk through it. So I'm trying to prove that the eigenvalues of a triangular matrix are just the entries on its main diagonal. And this will come in handy next time, because what we're going to do is we will want to, again, use triangular matrices for something specific. It's going to be how do we find the eigenvalues if I didn't give you any, okay? We'll talk about something called a characteristic polynomial. But I did it with a little 3x3 real quick. So I'm proving that it's true for an upper triangular because the lower triangular would be the same. So I wrote an upper triangular 3x3 matrix. You could also do this with more entries. I was just too lazy to write out the dot, dot, dots. And I'm letting lambda be an eigenvalue for a. So that means if I was searching for solutions, I'm searching for solutions to a minus lambda I times x equals 0. So I went ahead and made the matrix a minus lambda I. So I just subtracted, that only changes the diagonal entries. And then what I would do next is I would row reduce this matrix to find the solutions. Since the trivial solution cannot be the only solution, okay, we need there to be free variables, which means that one of these diagonal entries cannot be a pivot, at least. It could be more than one, okay? Which means that one of these diagonal entries has to be equal to 0. So I went ahead and I set them all equal to 0. But then solving those equations meant that in order to make one or more of those diagonal entries equal to 0, that meant that the diagonal entries themselves had to be the lambda I was looking for. One of them had to be a lambda. That was the eigenvalue. Okay? So that means that the diagonal entries, okay, that would give us free variables along the diagonal, okay, are in fact the diagonal entries. Okay, so we have lambda equals a11, that is a possible eigenvalue. Lambda equals a22, that is an eigenvalue, or lambda equals a33. If they're all the same number, then great, we have one eigenvalue. If they're two different numbers, great, we have two different eigenvalues, something like that. But key thing is they were all along the diagonal because that's where the pivots were. That's where we needed to get rid of one or more pivots so that there would be free variables, so that we would get a non-trivial solution. Okay? All right, hopefully that makes, if you have questions on that proof, let me know in office hours. All right, and last thing, okay, I guess I'll just keep going. What are the eigenvalues? This was our example. Now, again, key reminder here, this is only going to work for triangular matrices. So I want to make sure that before I use my trick, I am looking at a triangular matrix. So here I am looking at an upper triangular matrix because below the diagonal I have only zeros. Above the diagonal, I don't care what's happening. Okay, but below the diagonal, okay, the entries are 0, okay, and that means that this is an upper triangular matrix. That means that my eigenvalues are on the diagonal. They're 0, 3, and -2. Okay, here I am looking at a lower triangular matrix because the entries above the diagonal are zeros. So again, since it's a lower triangular matrix, my eigenvalues are on the diagonal, 5, 0, and 3. Again, it is okay for an eigenvalue to be 0. Okay, that's okay. It is not okay for an eigenvector to be the 0 vector. That's what we don't want. Okay. All right, so there was one last theorem on the back, okay, but I sent it to the textbook for that proof. If, and this is why we are able to form a basis. So if these vectors, v1 through vr, are eigenvectors that correspond to distinct eigenvalues, okay, then that is a linearly independent set. Okay, that's why we're able to form a basis. If you need more proof for that, go to 270. Okay, but we kind of did some examples where you can see that. All right. There's more practice on the back, but we're already 30 minutes, so I'm going to stop here, and I'm going to encourage you to look at the filled notes to do these examples. Okay, 3 really simple examples on the back, or look for the homework.